Hello one and all, and welcome to the Math Magic Show. In this one we're going to take a look at deciphering the mystery of the following. So it says there e raised to the I, and then within parentheses we have kx minus vt. This is an expression that represents a moving wave. Now when you look at it, it absolutely does not look like anything that is remotely related to waves. Let's break this down and I'll illustrate how it actually does represent a moving wave. So here the first stage would be to observe the following, that there's an identity that says e to the I theta equals cosine theta plus I sine theta. Now in our context, what plays the role of theta? Well, it's kx minus vt. That plays the role of theta, which means that that expression across the top can be written equivalently as follows. E to the I multiplying kx minus vt equals cosine kx minus vt plus I. The I is the imaginary unit, please remember that. Sine kx minus vt. So here in this context we have to define the meaning of our quantity. So the x you can imagine is like a space variable, and t is time, the v is the speed of the wave, and the k is sometimes called the wave number. In other words, it tells you, for example, how many cycles fit within 2 pi units. That's a lot. So what we're going to do is just actually simulate this using simple values for k and v, and we will leave x and t. This is what I mean. Take a look. To make things go as simply as possible, I'm going to let k equal 1. That means basically 1 cycle per 2 pi along the x-axis, in other words. So that's the basic sine wave. We'll see in a second why that is the case. After that, that v equals 1, I'm setting v equals to 1. It's just an arbitrary choice that I'm making for both k and v. I could make k 10 and v 50. These are just some arbitrary values, the simplest ones I can find to help us understand what's happening. So what this 1 indicates is that the wave moves 1 unit to the right per 1 unit of time. That's what it means. Again, this is all still kind of abstract, right? Let's break it down a little bit more in some detail. What I'm going to do is I'm going to rewrite things as follows. Instead of writing kx minus vt, I'm replacing k with 1 and v with 1. That's going to give me cosine 1x minus 1t plus I sine 1x minus 1t. Now when you look at these two pieces, cosine and sine, if you think about it, those are just basic cosine and sine functions. Everything in math often can be reduced to something relatively simple. It's just when you first encounter an expression like this, e to the I kx minus vt, it is abstract. Then you just have to unpack it, study it a little bit, and you'll see there's usually some relatively simple concept operating under the surface. So here, what I'm going to do is this. Because cosine 1x minus 1t plus I sine 1x minus 1t, that's basically a complex number if you think about it. This cosine 1x minus 1t represents the real part, and the sine 1x minus 1t represents the imaginary part, because it's the part multiplying the I. Now in mathematics, we can indicate that by writing something like this. So I'm writing here RE and then a quantity. What that says simply in simple English is just take the real part out and separate it. So that the real part is cosine 1x minus 1t. And then you can imagine doing this with the imaginary part. So when I do that, I will have the following there. Imaginary part of e to the I 1x minus 1t is just the sine 1x minus 1t. So all of this so far is just unpacking that first expression that we have on top. Now at this point, what we can do, because we have basically a cosine and a sine, we could study each one individually, and that's it, and show how each one represents a moving wave. So in order to save some time perhaps, I will focus just on the imaginary part, which is 1x minus 1t, and let's see how exactly that represents a moving wave. So let's continue. So I'm going to use sine 1x minus 1t, that's the imaginary part of our expression there. And the first thing that we do to model what happens is simply set t equal to 0. So when I do that, in other words, it's like evaluating at t equals 0. So I will have sine of x minus 1 times 0. 1 times 0, of course, is 0, so we end up with sine of x. That's a basic sine function. That's all it is. So at t equals 0, at time equals 0. If you were to sketch it, of course, it would look like this. This is a basic sine function. Nevertheless, let's remind ourselves what's happening here in this basic sine function. So some key points. This blue point above my head, I hope you can see it's above my head there. That's 0, 0. And this black point basically represents the end of a single cycle. The red tracing there represents a single cycle. And the black point, in terms of its horizontal position, is at about 2 pi, which is 6 point something or other. And I know that because if you look down over here, above my head, or right up next to me, you see there's a 6. So it's about 6 units along the x-axis. That completes one cycle. So at t equals 0, we have a wave that looks like this. Now let's see what happens when we increase t by 1. That's the next goal. So when I increase t by 1, I'm going to have something that looks like this. It's going to say evaluating at t equals 1. That's going to give me sine of x minus 1 times 1. But that's just going to give me sine of x minus 1. Now perhaps you remember from basic high school algebra that basically represents the sine curve shifted by 1 unit to the right. That's all it is. If you think about it from that perspective, complex numbers and then are shifting sines and cosines around, this is all essentially at the level of perhaps, like college algebra or something along those lines, pre-calculus say, okay? No calculus. So next, what does this represent? It means the following, that relative to the last stage, our red cycle has moved 1 unit to the right. That's what it means. So when the time transitions from time 0 to time 1, the red curve, the red cycle, the whole sine curve, in fact, moves by 1 unit to the right. This is also called a phase shift. So the blue point moves by 1 unit to the right. Any other point on that red curve moves by 1 unit to the right. All of the points in the whole curve. That means that the black point also moves by 1 unit to the right. Remember that originally that was at about 6 point something. Now it's at about 7 point something. So again, also moving 1 unit to the right. Let's continue though, take a look. One more time, we want to really get at the essence of it. So imagine that you now plug in t equals 2. That's going to give you sine of x minus 1 times 2, which is the sine of x minus 2. That's just a basic sine curve shifted 2 units to the right. That's all it is. So when I work this out, take a look. There's a horizontal shift of 2 units to the right. For in trig, this is often called, again, a phase shift, not a horizontal shift. But that's all it is at the level, perhaps, of just college algebra, just a horizontal shift, or algebra in trig. That means that this blue point now, relative to where it started, is 2 units to the right of it. You see, that's at the origin itself, right above my head there. I hope that looks like it. And then I move over here 2 units to the right. But again, this means that the whole curve, like a rigid wire, has moved 2 units to the right. So that means that this black point is now also 2 units to the right with respect to sine of x. That's what this sine of x minus 2 indicates. Take the sine and move it 2 units to the right, and that is how you create that kind of effect of a moving wave. Don't think of it as anything fancy, think of it as a simple animation, that's all. One more time, just to stress this point, make sure we get it. So evaluate at t equals 3, that's going to give you sine of x minus 1 times 3, which is sine of x minus 3. That represents a curve that has moved 3 units to the right with respect to the basic sine curve. So here in the picture it's going to look like this. You have here a space of 3 units to the right. That is, in other words, the whole curve has moved 3 units to the right. I arbitrarily decided to focus with the red tracing as just one cycle so we could emphasize that fact. So the blue point moves 3 units to the right. This also means that the black point now is 3 units to the right of where it started with respect to the sine x function, the parent graph. Now, I've done all of this using the sine curve, which happens to be, in this case, the imaginary part of our expression. But I could have easily repeated this with the cosine curve, obtaining something very similar. So let's put all of these together now with just one last picture so we can visualize everything in one full go. It looks like this. So this is sine of x. This is sine of x minus 1. So I'm shifting, you see? It's like a little animation. Remember the old-fashioned things, right? You draw a picture and then you flip really fast and it's going to create the appearance of motion. That's all this is. Okay, and then here I'm going to have 2 units to the right and then 3 units to the right. And if you look at them really fast, through that full cycle, you will see how it kind of seems to slide over. I deliberately avoided making an actual animation because then I think it can actually obscure some of the essence. You just have to do it when you're studying it for the first time in small, discrete stages. And once you've got that in place, then you can try to look at for animations and make the motion appear to be continuous this way, okay? Alright, well, that is it for me. Thank you so much for watching. I hope it's been helpful and insightful and you've learned something useful here. Please leave a like and subscribe, and I will see you in another mathematical video.